Welcome! Today, we'll explore an interesting problem titled Number 2215. Find the difference of two arrays. In this problem, we'll dive into techniques to identify unique elements between two arrays, leveraging efficient algorithms to solve it. Let's get started. In this problem, you are given two integer arrays, nums1 and nums2. Your task is to return a list that consists of two separate lists. The first list should contain all the distinct integers that are present in nums1 but not in nums2. Similarly, the second list should contain all the distinct integers that are present in nums2 but not in nums1. It's important to note that each list should only include unique integers, meaning no duplicates, and the order in which the lists are returned does not matter. For the input, both arrays have lengths between 1 and 1000, and their elements can range from -1000 to 1000. The output will be this list of two lists, where the first represents the unique integers from nums1 not found in nums2, and the second represents the unique integers from nums2 not found in nums1. Let's look at an example to better understand the problem. Suppose nums1 is 1, 2, 3, and nums2 is 2, 4, 6. The integers in nums1 that are not in nums2 are 1, 3, and the integers in nums2 that are not in nums1 are 4, 6. Since we are required to return these as two separate lists, the output will be 1, 3, 4, 6. This demonstrates how the solution captures the unique elements from each array that are missing in the other. Now, consider another example where nums1 is 1, 2, 3, 3, and nums2 is 1, 1, 2, 2. Here, the integers in nums1 that are not in nums2 are 3. Notice that duplicates are ignored, so even though 3 appears twice in nums1, it only appears once in the output. On the other hand, all the elements in nums2 are also present in nums1, so there are no unique integers in nums2 that are not in nums1. This results in an empty list. Therefore, the final output is 3. This example highlights the importance of ignoring duplicates and ensuring each list contains only unique values. Additionally, there are some edge cases to consider. For instance, if one of the arrays is empty, the output will simply include all unique elements from the non-empty array in the respective list. For example, if nums1 is empty and nums2 is 1, 2, 3, the output will be 1, 2, 3. Similarly, if nums1 is 4, 5, 6, and nums2 is empty, the output will be 4, 5, 6. Another edge case arises when both arrays contain exactly the same elements. In this situation, since there are no unique integers in either array, the output will be. Finally, remember that duplicates in the input arrays must be ignored, as the output only requires distinct integers. To tackle this problem, we begin by considering different approaches. The most straightforward is the brute force method. Here, the idea is simple. For each element in the first array, we check if it exists in the second array. If it doesn't, we add it to a result list. Similarly, for each element in the second array, we check if it exists in the first array, and if not, add it to a separate result list. Finally, we return these two lists as our result. While this method is easy to understand and implement, it's not efficient for large input sizes. The nested iteration leads to a time complexity of n squared, making it impractical for arrays with a significant number of elements. Additionally, it has a space complexity of n, as we need storage for intermediate results. This approach is a good starting point for understanding the problem but is not scalable in real-world scenarios. Instead, we need a more optimized solution. To improve efficiency, we can use Python's set data structure. Sets are highly advantageous here because they automatically remove duplicates and allow constant time lookups on average. The main idea is to convert both input arrays into sets, which we'll call set1 and set2. The difference between these sets can then be calculated directly. Set1, set2 gives us the elements in the first array that aren't in the second, while set2, set1 gives us the opposite. Once we have these results, we convert them back into lists to match the required output format. This method is much faster, with a time complexity of n plus m, where n and m are the sizes of the two arrays. The space complexity is also n plus m, due to the storage needed for the sets and the output. This approach is not only faster but also straightforward to implement, making it ideal for handling large datasets. However, it does require additional memory for the sets, which is a trade-off we accept for the sake of performance. Another optimized method involves using dictionaries to count occurrences of elements in the arrays. By iterating through each array, we populate dictionaries that track the frequency of each element. Then, we use dictionary lookups to identify elements that are unique to one array or the other. This approach has a similar time and space complexity to the set-based method, O, n plus m, but it introduces additional complexity due to the need for bookkeeping. While dictionaries offer an alternative solution, they are less intuitive and involve more steps than the set-based approach. After evaluating these options, we decided on the set-based strategy for its balance of simplicity and efficiency. Not only does it minimize runtime complexity, but it also avoids unnecessary complexity in the code. This makes it easier to understand, debug, and maintain, especially for large-scale inputs. The breakthrough insight in this problem lies in recognizing that set operations naturally solve the problem by removing duplicates and efficiently finding differences. This realization makes the set-based approach both optimal and elegant. By leveraging Python's built-in set functionality, we can achieve the desired result in minimal time and space. Here's the implementation of the chosen approach. We convert the input arrays into sets, calculate their differences, and then convert the results back into lists. This concise and efficient solution handles the problem with just a few lines of code. The key advantages of this method are its speed, simplicity, and scalability, making it the best choice for solving this problem. With this approach, we ensure that our solution is not only correct but also optimized for performance. To start, this problem asks us to find the difference between two arrays, nums1 and nums2. Specifically, we need to return two lists, one containing all distinct integers in nums1 but not in nums2, and the other containing all distinct integers in nums2 but not in nums1. Let's first explore the brute force approach for solving this. We begin by initializing two empty lists, unique underscore in underscore nums1 and unique underscore in underscore nums2, which will store our results. Then, to find elements in nums1 that are not in nums2, we iterate through each element x in nums1. For each x, we check if it exists in nums2 using a nested loop. If x is not in nums2 and hasn't already been added to unique underscore in underscore nums1, we append it to the list. This ensures we only include distinct elements. Similarly, we find elements in nums2 that are not in nums1 by iterating through nums2 and performing the same checks, but now for membership in nums1. Once both lists are populated, we return unique underscore in underscore nums1, unique underscore in underscore nums2, as the final result. The brute force approach works, but it is inefficient due to the use of nested loops, which result in a time complexity of O, n squared. To optimize the solution, we can use sets, which allow for faster lookups. The optimized algorithm begins by converting both nums1 and nums2 into sets, named set1 and set2. This conversion not only provides faster membership checks but also automatically removes duplicates. Next, we use set operations to compute the differences. The difference set1, set2 gives us all elements in nums1 but not in nums2, while set2, set1 gives us all elements in nums2 but not in nums1. These operations are highly efficient, with an average time complexity of O(1) for each membership check. Finally, we convert the resulting sets back into lists to match the problem's required output format and return them. Once the differences between the sets are computed, the final step is to return the results as two lists, list, set1, set2, list, set2, set1. This optimized approach provides several key insights. First, using sets is advantageous because their average time complexity for membership checks is O(1), and set operations like difference are highly efficient. This eliminates the need for nested loops, reducing the overall complexity to O, n plus m, where n and m are the lengths of the input arrays. Another benefit of converting arrays to sets is that duplicates are automatically handled, simplifying the logic. For edge cases, such as when one or both arrays are empty, the algorithm naturally handles these scenarios. For instance, if nums1 is empty, the output will be list, set, nums2. Similarly, if both arrays are identical, the result will be. These cases demonstrate the robustness of the optimized solution. Lastly, the simplicity of the data structures used, sets and lists, keeps the implementation clean and efficient. The choice of data structures plays a crucial role in the efficiency of this solution. Sets are used because they excel at performing fast membership checks in set operations, such as differences, with an average time complexity of O(1) for lookups and O(n) for operations like set differences. Lists are used for the final output because the problem specifies that the results must be returned as lists. The overall time complexity of this approach is O(n plus m), where n and m are the sizes of nums1 and nums2. This accounts for the time required to convert the arrays into sets and perform the set differences. The space complexity is also O(n plus m), due to the additional storage needed for the sets and the result lists. This ensures the algorithm is not only faster than the brute force approach but also remains space efficient. To illustrate, the Python implementation of the optimized approach is concise and straightforward. By converting the arrays to sets, computing the differences, and converting the results back to lists, we achieve an efficient and clean solution. The key operations in this optimized solution are straightforward yet powerful. First, converting the arrays to sets removes duplicates and enables fast operations. Then, using set difference operations allows us to efficiently find elements unique to each array without needing nested loops. Finally, converting the resulting sets back to lists ensures we meet the output format requirements. To understand how this handles edge cases, consider a few examples. When one array is empty, such as nums1 equals, and nums2 equals, 1, 2, 3, the result is 1, 2, 3, because all elements of nums2 are unique. For identical arrays, like nums1 equals, 1, 2, 3, and nums2 equals, 1, 2, 3, the result is, since there are no unique elements. In cases where there is no overlap, such as nums1 equals, 1, 2, and nums2 equals, 3, 4, the result is, 1, 2, 3, 4. These examples highlight the algorithm's ability to handle different scenarios effectively. When there is some overlap between the arrays, the algorithm still works seamlessly. For example, if nums1 equals 1, 2, 3, and nums2 equals 3, 4, 5, the output is 1, 2, 4, 5. Here, the algorithm correctly identifies 1 and 2 as being unique to nums1, and 4 and 5 as being unique to nums2, while ignoring the common element 3. This example demonstrates the precision of set operations in filtering out shared values. By leveraging the strengths of sets and maintaining the required output format with lists, the optimized approach handles all types of input efficiently. The combination of simplicity, speed, and robustness makes this solution an excellent choice for solving the problem. This Python solution efficiently solves the problem by utilizing sets to find the differences between two arrays. The find difference function is implemented within the solution class. First, the two input arrays nums1 and nums2 are converted into sets, set1 and set2. This ensures that all elements are unique, which automatically eliminates any duplicates from the arrays. This step is crucial as the problem specifies working with distinct integers. Next, the difference between these sets is calculated using set subtraction. The expression set1, set2 gives all elements that are in set1 but not in set2, and this result is converted into a list called diff1. Similarly, set2, set1 gives all elements that are in set2 but not in set1, and this result is stored in another list, diff2. Finally, the function returns a list containing diff1 and diff2 as its two elements. This matches the required output format of two lists, one for elements unique to nums1 and another for elements unique to nums2. This approach is efficient, with a time complexity of O(n plus m), where n and m are the lengths of nums1 and nums2, respectively. This is because converting arrays to sets and performing set operations both have linear complexity. The space complexity is also O(n plus m), due to the storage of sets and the resulting lists. Here, we start by importing the necessary Java utilities to work with sets and lists. The main function, findDifference, takes two integer arrays as input. The first step is to convert these arrays into sets. This is done using two set objects, set1 and set2, where we iterate through each array and add its elements to the respective set. This ensures that we have only unique elements, as sets automatically handle duplicates. Once the sets are prepared, we focus on identifying elements that are unique to nums1. To do this, we create an empty list called diff1. We iterate through each element in set1 and check if it is not present in set2. If the condition is true, we add that element to diff1. This gives us all the elements that are present in nums1 but not in nums2. The next step will be to apply a similar process for nums2. Now, to find the elements that are unique to nums2, we initialize another list called diff2. We iterate through each element in set2 and check if it is not present in set1. If the condition is met, we add that element to diff2. This gives us all the elements present in nums2 but not in nums1. Once we have both lists, diff1 and diff2, we combine them into a single result. We create a new list of lists called result, add diff1 as the first sublist, and diff2 as the second sublist. Finally, we return this result list, which contains the two lists of unique elements. This concludes the implementation, effectively solving the problem by leveraging sets for efficient comparison and lists for storing the output. To solve this problem, we start with example 1, where nums1 is 1, 2, 3, and nums2 is 2, 4, 6. The first step is to convert both arrays into sets. This gives us set 1 as 1, 2, 3, and set 2 as 2, 4, 6. Converting to sets is crucial because it removes duplicates, if any, and allows us to perform efficient set operations. Next, we find the unique elements in each set. Subtracting set 2 from set 1 gives 1, 3, which represents the elements present in set 1 but not in set 2. Similarly, subtracting set 1 from set 2 gives 4, 6, representing the elements in set 2 but not in set 1. Finally, we convert these sets back into lists. So 1, 3 becomes 1, 3, and 4, 6 becomes 4, 6. To complete the process for example 1, we return the result as a list of these two lists, 1, 3, 4, 6. This output represents the elements that are unique to each input array. Now, consider example 2, where nums1 and nums2 are both 1, 2, 3. After converting these arrays into sets, we get set 1 equals 1, 2, 3, and set 2 equals 1, 2, 3. Since the sets are identical, subtracting one from the other results in an empty set for both operations. Specifically, set 1 set 2 gives, and set 2 set 1 also gives. This means there are no unique elements in either array. Next, we convert the empty sets obtained in example 2 into lists. Both diff1 and diff2 become. With no unique elements in either array, the final output for this example is. Moving on to example 3, we examine the case where the arrays have completely disjoint elements. Here, nums1 is 7, 8, 9, and nums2 is 10, 11, 12. Converting the arrays into sets gives set 1 equals 7, 8, 9, and set 2 equals 10, 11, 12. Since there are no overlapping elements between the two sets, each set entirely consists of unique elements. In example 3, subtracting set 2 from set 1 gives diff1 equals 7, 8, 9, because all elements of set 1 are unique. Similarly, subtracting set 1 from set 2 gives diff2 equals 10, 11, 12, because all elements of set 2 are unique. Converting these sets back into lists, diff1 becomes 7, 8, 9, and diff2 becomes 10, 11, 12. The final result is 7, 8, 9, 10, 11, 12, representing the unique elements from each input array. This illustrates how the solution handles arrays with no overlapping elements, ensuring all unique elements are correctly identified and returned. In this problem, we calculate the difference between two arrays by converting them into sets and performing set operations. To analyze the time complexity of the solution, let's break it down into its key steps. First, we convert the input arrays, nums1 and nums2, into sets, which we call set1 and set2. The conversion process involves hashing each element of the array and inserting it into the set. If nums1 has n_1 elements and nums2 has n_2 elements, this step takes O, n_1, and O, n_2, time, respectively. Next, we perform set difference operations, such as calculating set1 minus set2 and set2 minus set1. These operations iterate over the elements of the first set and check for membership in the second set. Since membership checks in a set are O(1) on average, the overall complexity for these operations is proportional to the size of the first set. Specifically, the complexity is O, set1, for the operation set1, set2 and O, set2, for set2 set1, where set1 and a set2 represent the number of unique elements in nums1 and nums2, respectively. After computing the set differences, the next step is to convert the resulting sets into lists, which are returned as the output. If the size of the set difference set1, set2 is k_1 and the size of set2, set1 is k_2, converting these sets to lists takes O, k_1, and O, k_2, respectively. To summarize the time complexity of the entire solution, we add up the complexities of all the steps, O, n_1, for converting nums1 to set1, O, n_2, for converting nums2 to set2, O, set1, for the first set difference, O, set2, for the second, and finally O, k_1, and O, k_2, for converting the resulting sets to lists. Since set1 is at most n_1, set2 is at most n_2, and k_1 and k_2 are at most n_1 plus n_2, the overall time complexity simplifies to O, n_1 plus n_2. This efficiency is achieved by leveraging the properties of sets for fast operations. Now, let's analyze the space complexity of the solution. The first major component of space usage comes from the sets we create. Set1 requires O, set1, space, which is proportional to the number of unique elements in nums1. Similarly, set2 requires O, set2, space, proportional to the unique elements in nums2. The second component of space usage is the output lists, diff1 and diff2. These lists require O, k_1, and O, k_2, space, where k_1 and k_2 are the sizes of the set differences set1, set2 and set2, set1, respectively. Finally, the algorithm does not use any additional data structures apart from these sets and output lists, so any extra or auxiliary space usage is minimal. This streamlined use of memory ensures that the solution remains efficient in terms of space. When we combine all these factors, the overall space complexity of the solution becomes O, set1 plus set2 plus k_1 plus k_2. Since set1 is at most n_1, set2 is at most n_2, and k_1 and k_2 are at most n_1 plus n_2, the space complexity simplifies to O, n_1 plus n_2. Let's compare this optimized approach to a naive solution. In a naive approach, we might use nested loops to compare each element of nums1 with each element of nums2. This would result in a worst-case time complexity of O, n_1 asterisk n_2, which is significantly slower for large inputs. The naive approach could save space with O(1) usage if no additional data structures are used, but this comes at the cost of inefficiency in terms of execution time. The optimized solution, on the other hand, uses additional space for sets but achieves much faster computation, with both time and space complexities reduced to O, n_1 plus n_2. To summarize the complexity analysis, the optimized solution has a time complexity of O, n_1 plus n_2, and a space complexity of O, n_1 plus n_2. These efficiencies are achieved through the use of hash-based set operations, which eliminate the need for nested iterations. By converting the input arrays into sets, we take advantage of the constant time average complexity of set operations, making the solution significantly faster than a naive approach. This makes the algorithm highly effective for large input sizes while maintaining a reasonable trade-off in memory usage. Overall, the optimized approach demonstrates the power of leveraging data structures like sets to simplify and accelerate computations in array manipulation problems. When solving this problem, there are several common mistakes to watch out for. First, relying on nested loops for large inputs is a frequent pitfall. While this brute force approach might be acceptable for small arrays, it becomes highly inefficient as input sizes grow, leading to an O(n*m) time complexity. Instead, use data structures like hash sets or sorting to optimize performance. Another issue arises with duplicates. If the problem requires working with unique elements, failing to handle duplicates properly can result in incorrect outcomes. To address this, use a set to automatically eliminate duplicates or pre-process your data to remove them explicitly. Edge case handling is another area to be cautious about. Scenarios like empty arrays, arrays with all identical elements, or arrays of vastly different lengths can expose flaws in your solution. Be sure to test these cases thoroughly. Misinterpreting set operations can also lead to logic errors. For example, confusing set1.difference, set2, with set2.difference, set1, could produce the wrong results, so it's vital to understand these methods clearly. Lastly, overlooking input constraints such as maximum array sizes or value ranges can cause solutions to fail during performance testing. Always keep these constraints in mind to ensure your code is robust. Now, let's talk about how to approach this problem effectively, especially in an interview setting. Hash sets are incredibly useful here, as they allow you to perform operations like membership checks or finding unique elements with a time complexity of O(n). For instance, if you're tasked with identifying elements unique to one array, using sets can significantly reduce complexity compared to nested loops. Beyond efficiency, interviewers value solutions that balance readability with performance. While speed is important, your code should be clear and maintainable. Be ready to discuss the trade-offs you made between clarity and optimization. It's also critical to communicate your thought process. Start by outlining the brute force approach to establish a baseline, then explain how you improved it using sets, sorting, or other techniques. This not only demonstrates your problem-solving skills but also shows your ability to analyze and refine solutions. Additionally, familiarize yourself with variations of the problem. For example, you might be asked to find common elements between two arrays, which is an intersection operation, or to combine elements from both arrays, which is a union operation. Being prepared for these variations ensures you can adapt your solution quickly. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 349 focuses on finding the intersection of two arrays, while LeetCode 350 is a variation that handles intersections with duplicates. LeetCode 448 asks you to find all numbers missing from an array, and LeetCode 1365 challenges you to determine how many numbers are smaller than the current number. These problems build on similar concepts and broaden your problem-solving toolkit. Additionally, there are alternative approaches you can consider depending on the requirements. A sorting approach, where you sort both arrays and use two pointers, is effective for problems involving uniqueness or intersections. While this method has a time complexity of O(n log n plus m log m, it's often simpler to implement than hash-based solutions. If you need to account for frequencies, such as when handling duplicates and intersections, hash maps are a great choice. They allow you to count occurrences efficiently with a complexity of O(n plus m, though they may use slightly more memory than sets. Finally, for problems involving a limited range of integers, bit manipulation can be an elegant solution with constant space usage. However, this method is less intuitive and harder to implement, so it's typically reserved for very specific scenarios. By understanding these trade-offs, you can choose the best approach for the problem at hand. Great job! To recap, we explored the problem of finding the difference of two arrays. You've learned how to use hash sets effectively and weigh the pros and cons of different approaches. Keep practicing, every challenge is a step toward mastery. Thanks for watching, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!